Welcome to Crash Course. We are discussing current electricity in today's class. Let us first revisit the important concepts, understand the equations, and familiarize ourselves with the basic ideas. The basic idea of electric current arises from the fact that charges in motion constitute electric current. So, I is equal to Q divided by T. And if you consider this is basically due to a steady flow of charges. If the flow is non-steady, we write I as dQ by dt. This is the case of variable current. This current, which basically is a scalar quantity, can also be represented in terms of current density. Its representation in terms of a vector quantity can be in terms of current density. So, what is that current density? You may wish to recall current density J is nothing but current per unit area, normal area. For example, if I consider the current to be flowing along this direction, then we consider an area which is perpendicular to this is taken as current density. So, current density is current per unit perpendicular area. It may so happen that the current is different at different points. So, in such cases, we can write the equation in the following forms. Observe that current is written as J into A perpendicular, or this can also be written as I is equal to J dot A. Dot product is in terms of cos theta, therefore I is equal to J dot A. This can also be written as dI. The current density can also be represented in terms of current over a smaller area, small part, and that gives rise to J dot dA, or the total current enclosed because of this variable current density can be written as J dot dA. So, current can be represented in terms of current density in this form. In order to get the total current, you can integrate it. The microscopic picture or microscopic details of electric current is generally in terms of what happens inside a solid conductor. You know that it is the random motion which takes place inside a solid conductor, but the random motion does not give rise to electric current. It is the systematic motion. The systematic motion is represented in terms of drift velocity. Drift velocity Vd is given by EE divided by m into tau, where tau is the relaxation time. This can also be written as mu into E, where mu is the mobility of the electrons. And if I take that into consideration, the current density can be written as I divided by A, that becomes NE Vd, or I can also write it as NE into mu E, or this is sigma into E. This is your Ohm's law. Ohm's law in microscopic form. This is Ohm's law in microscopic form. So, you can write E is equal to rho into J, where 1 by rho is sigma, and E is equal to rho into J. This is called the microscopic form of Ohm's law, or say the representation in terms of electric field, current density, and of course resistivity rho. This can also be represented as V is equal to I into R. This is your macroscopic form of Ohm's law, where V is the potential difference, I is the current, and R is the resistance. This electrical resistance is the property of a substance due to which the flow of electric charges is opposed. electrical resistance depends on the dimensions of the given object, temperature, and the nature of the material. This resistance rho is given by rho L divided by A, where rho is the resistivity of the material, L is its length, and A is the area of cross section. For example, if you want to measure the resistance between the ends A and B, then you need to take the length along this direction and area perpendicular to it. So remember this idea, the area needs to be taken perpendicular to it, length needs to be taken along the direction. Ohm's law can be shown graphically like this. V versus I graph is a straight line passing through the origin, and the slope, that is delta V divided by delta I, clearly is resistance. And in the case of non-linear conductors, for example, if the potential difference versus current graph is like this, then the slope at that particular point gives you the resistance, which basically is a dynamic resistance. This resistance depends on various parameters. One such parameter is temperature. How does the temperature affect the resistance? The temperature dependence of the resistance is given by RT is equal to R naught into 1 plus alpha theta, or so I can write R theta is equal to R naught into 1 plus theta, where theta is the temperature. And we can also write resistivity rho as rho naught into 1 plus alpha theta, where alpha is the coefficient of temperature coefficient of resistance. This is the property of a material, and the SI unit of alpha is per degree centigrade or per Kelvin. So in order to analyze very simple circuits, Ohm's law alone is sufficient. That means you can have potential difference, you can have current, and you can have resistance related by V is equal to IR. For example, you can consider a simple case like this. You have resistance, you have a source of potential difference, and the current in the circuit I, the potential difference V and R can be related simply through this equation V is equal to I into R. However, in order to analyze complex circuits, the Ohm's law alone is not sufficient. Ohm's law alone does not suffice. In such cases, we have to resort to other tools. And one such tool is the usage of what is known as Kirchhoff's law. The two laws, first is Junction Law, or this is also known as nodal analysis, or say node law. According to this, the net current at a junction is equal to 0. Or we can say the incoming current, the current entering the junction is equal to current leaving the junction. Current entering is equal to current leaving. Second is Kirchhoff's voltage law or loop law, according to which the net change in potential over a loop is 0. Net change in potential is 0. Now the net change in potential involves perhaps the changes across the resistors and changes across the EMF sources. So we need to have a simple sign convention here. This is very simple. Across a resistor, if you are going along the direction of the current, then there is a drop in potential. And if you are going against the current, then there is a rise in potential. Likewise, across a cell, if you are going from positive terminal to negative terminal, then there is a drop in potential, and if you are going from negative terminal to positive terminal, there is a rise in potential. Simple, very simple rules. So with the help of Ohm's law and Kirchhoff's law, it is pretty easy to analyze the circuits and obtain the unknown, like maybe current, maybe voltage, maybe resistance, etc. But many a times what happens is that perhaps you are given the resistors connected in various possibilities. For example, if the resistors are connected in series, you have a situation here, resistors are R1, R2 and R3 and the potential difference is V, then a series combination, as you all know, is identified by same current in the circuit. As the currents are same, the potential differences are different, V1, V2, V3. So we can write V1 plus V2 plus V3. That means we can write this is equal to V. So we can write I into R1 plus R2 plus R3 is equal to I into R effective or equivalent. That means I am going to replace this these three resistors by one resistor whose value is such that it supports the same current when connected across the same source. So I have R equivalent in series combination as R1 plus R2 plus R3. So also remember, in this case V1 is to V2 is to V3 is equal to R1 is to R2 is to R3. Because the currents are same, we can write it this way. The voltage is directly proportional to resistance. For example, you have this situation, you have two resistors R1 and R2, and imagine that this is the voltage source. If V1 is the voltage across this and V2 is the voltage across this, then we can write V1 is equal to R1 divided by R1 plus R2 plus R3 etc. into V, and V2 is equal to R2 divided by R1 plus R2 plus, we have only R2 here, into V. So remember the usage of this simple equation. If there are two identical resistors, R and R each connected in series, then the equivalent resistance is 2R, and if there are n identical resistors, R each all connected in series, then the equivalent resistance is R times or n times R. In parallel, what if the resistors are connected in parallel? We have a couple of resistors R1, R2, R3 etc. and they are all connected in parallel across a source. You know that the combination is said to be parallel if the voltages are same across them, which implies that the currents are different. So a parallel combination is identified by the fact that the voltages are same and the currents add. Therefore, the net current is given by I1 plus I2 plus I3 etc. and the equivalent resistance is given by 1 by R is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And if there are two resistors, for example R1 and R2 connected in parallel, then the equivalent resistance is given by R1 R2 divided by R1 plus R2, and the currents are in the ratio 1 by R1 is to 1 by R2 is to 1 by R3. So remember, a very useful formula. For example, we have an arrangement like this, R1 and R2, and here is the source, and let's assume that the currents are I1 and I2. Then the currents can be represented like this. I1 is equal to, if the main current is I, then it is main current into resistance of the other branch divided by the sum of the resistors. Likewise, I2 is equal to I into R1 divided by R1 plus R2. So this simple idea can be quite useful when you are solving problems. This branch current formula is quite useful. For example, let us consider two resistors which are connected in parallel, R and R. What is the equivalent resistance? R by 2. If there are n such identical resistors all connected in parallel, then the equivalent resistance is R divided by n. These ideas are regarding resistors. Just like resistors, sources of EMF can be analyzed. For example, let us consider a source of EMF. Source of EMF or a cell in general is an arrangement which can provide the potential difference. This is represented by E. It also has some amount of finite internal resistance. This is as good as an ideal cell and a resistor are connected across its terminals. So a real cell is equivalent to an ideal cell plus an internal resistor. It can be shown like this. If such a cell is taken into consideration, this is E, this is R. Remember, this is the cell. What I am talking of is a cell now. And assume that this is connected to an external resistor R. Then the current in the circuit is given by E divided by R plus R. And the potential difference between the two terminals, for example A and B, can be written in various forms. This can be written as E divided by R plus R. Or potential difference AB can also be written as E minus IR, where IR is the drop across its internal resistance. So potential difference AB, which is also called as terminal potential difference, is nothing but E minus IR. So terminal voltage or terminal potential difference is nothing but the EMF minus IR. Here a couple of important points which should be kept in mind are like this. If R is equal to 0, notice the cell becomes ideal. The cell becomes ideal, that means VAB simply becomes E. Likewise, if I is equal to 0, again VAB is equal to E. Now you notice that VAB appears to be less than E, that is true. But this is true only when the cell is in discharge mode. The cell is in the discharge mode. However, if the cell is in charging mode, then VAB is greater than E. So in such a case, it is given by E plus IR. For example, look at this cell, which is actually getting charged from another stronger cell. Then this is the direction of the current and the cell is said to be in the charging mode. So if the cell is in the charging mode, then the terminal potential difference is given by E plus IR. Or in general, we can write terminal potential difference is E plus or minus IR, plus when it is in the discharge mode and minus when it is in the discharge mode, plus when it is in the recharge mode. The cells can be connected in series or they can also be connected in parallel. Suppose we consider a couple of cells connected in series like this and assume that there is an external resistor R. This is ER, 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 etc. Then the current in the circuit is NE divided by, let's assume that there are N such cells, NE divided by R plus N into R. Now if NR is very small compared to R, then the current becomes NE divided by R. NE divided by R. You can also notice that if the combination is in parallel, the situation is different. For example, let us consider this arrangement ER, etc. There are n such cells and an external resistor R is connected. And in this case, the current is given by E divided by R plus R divided by N. Or I can use a different symbol here. I can use M here. So R divided by M. Or this becomes ME divided by MR plus R. So if MR is much less than R, then I becomes ME divided by R. So keep these basic ideas in mind. Suppose you consider a multiple combination. That means series as well as parallel combination. For example, you can consider it like this. Identical cells. There are, assume, M cells. Okay. And there are N such rows. And this entire combination is connected across an external resistor R. And each cell is of E, R. Then we can think of this entire arrangement like this. The current I becomes ME, that is the EMF of each row, divided by external resistor is R and net internal resistance. What is that? Due to each row I have MR and there are n such rows, so R plus MR divided by n, or this reduces to NME divided by NR plus MR. Now, if current is to become maximum, then NR is equal to MR, or we have R is equal to MR divided by N. That means current is maximum when net external resistance is equal to net internal resistor. This is what is known as maximum power transfer theorem. So according to maximum power transfer theorem, power transfer to a group of cells, by a group of cells to an external resistance is maximum when net external resistor is equal to net internal resistor. There are a couple of important applications here. What are all those important applications? Number one, what is called as Wheatstone's network. What is that Wheatstone's network? A Wheatstone's network is an arrangement of 5 resistors connected in the form of a bridge like this. We can call the resistors as R1, R2, R3, R4 and R5 and assume that this entire setup is connected to an external resistor. Now, this Wheatstone's network is said to be balanced if R1 by R2 is equal to R3 divided by R4 or R1 by R3, you notice, is equal to R2 by R4. That means if the adjacent resistances are in the same ratio, we say it is a balanced network. If it is a balanced network, then the central resistor R5 is as good as absent. So it has no role to play. Which means that that resistor can be dropped from all our calculations. So this is what I am left with, R1, R2, R3, R4. This is the network. So in order to reduce the circuit, simplify, you can take R1 and R2 to be in series, R3 and R4 to be in series, R1, R2 which are in series is in parallel with the combination of R3 and R4. It is a very simple thing. Suppose the Wheatstone's network is unbalanced. This is the network. R1, R2, R3, R4, R5. This point is A, this is B, this is C, this is D. Now let's assume that R1, R4 is greater than R2, R3. So first of all, we have noticed that R1 by R2 is not equal to R3 by R4. Remember it. So now if R1, R4 is greater than R2, R3, then potential at C is less than potential at D. If R1, R4 is less than R2, R3, then VC is more than VD. So remember this. This is a very important result. But in order to analyze these circuits, you will have to go for Kirchhoff's law. A simple rule like Ohm's law doesn't suffice here. We will have to go for Kirchhoff's law to analyze such circuits. But if it is balanced, notice that the current through R5 is 0 and the presence or absence of R5 makes no difference as far as the circuit is concerned. One of the very important applications of this is what is called as meter bridge. We can show the meter bridge like this, a representative idea. This is a wire of length L, or say 1 meter, and here is a resistor P, and here is one more resistor Q. I can call it as P and Q, and there is a sliding contact connected to galvanometer, and this is connected to a source of potential difference. And we start sliding this contact starting from the left end A, and I go up to the end C. Now at some point B, the galvanometer shows 0 reading. Let's assume that this length is L. Then the other length is 100 centimeter minus L. Now as the current through the galvanometer is 0, it resembles a Wheatstone's network, and therefore I can say P divided by Q is equal to L divided by 100 minus L. Therefore, the unknown resistance can be calculated. For example, Q. If Q is an unknown, I can calculate the value of Q. So Q will be equal to P into 100 minus L divided by L. So unknown resistance can be calculated using this very simple idea. Another important application is what is called as potentiometer. What's a potentiometer? It's basically a linear conductor of uniform cross section with a steady current set up in it. So we can show the construction like this. Here is a wire, and we maintain a constant current using some source, and this is your primary circuit using the EMF E. Now we have another cell, say some E dash, and this is connected to a galvanometer whose other end has a sliding contact. Now this is say some A, this is B, and I can slide this wire from A to B, and for a particular position the balance happens. Particular position balance happens. Suppose L1 is this length. Now I can say E dash is directly proportional to L dash, or say E is directly proportional to L. So I can first find out what the EMF is, proportional length is, E dash is proportional to L1. I can replace it by another cell E double dash which is proportional to L2, or I can say E dash divided by E double dash is equal to L1 by L2. So a very simple idea, we can use this to measure, rather compare the EMF of two different cells. We can use it to measure, compare the EMFs of two cells. Ammeter is nothing but a modified form of galvanometer. This is used to measure current. Galvanometer can measure very small current. Now, how to convert a galvanometer into an ammeter? You know that an ammeter is always connected in series and the ammeter has a very, very low resistance. So, these are the two requirements. To convert a galvanometer into an ammeter, what are you going to do? You are going to connect a low resistance in parallel. A low resistance is connected in parallel. This is what is called as shunting. For example, we can show like this, galvanometer, and we can connect a low resistance S, shunt resistance S in parallel. The main current is I, the current through the galvanometer is Ig. So, how much shunt resistance should be connected? This is given by Ig into G divided by I minus Ig, where G is the resistance of the galvanometer. So, if I know the resistance of the galvanometer, I can find out what should be the shunt resistance to be connected to convert it into an ammeter of known range. An ammeter of known range. Voltmeter, is an arrangement which can measure the potential difference, and therefore it is connected in parallel across the device, and this should have a very high resistance. How to connect a galvanometer into a voltmeter? To connect it, for example, I have the galvanometer here, and to connect it into a voltmeter, I'll connect high resistance in series with this. High resistance in series with this. This entire setup is what is now called as a voltmeter. Suppose the current is I, this Ig. So, we can say the resistance required can be calculated easily. Now, Ig is equal to V divided by R, that is galvanometer resistance plus R. So, we can say G plus R is equal to V by Ig, or the resistance required is V by Ig minus G. So, in order to convert a galvanometer into a voltmeter, we need to connect a high resistance in series, and the resistance required is given by V by Ig minus G. Electrical power. The energy liberated per second in a device, is called as power. That's right. The electrical power dissipated by a device is given by V into I, where V is the potential difference across the device and the current in it. If the current enters the higher potential point of the device, then power is consumed by it. That means it acts as a load. If the current enters the lower potential point, then the device supplies the power. That means it acts as a source. The power consumed is given by Vi, and this can also be written as I square R, or this can also be written as V square by R. So remember, all of them are interchangeable, but while solving the problem, you should be a little careful. You should look at the quantity which is constant and try to handle it. This power may result in heating also. So this heating dissipates an energy. Suppose energy dissipated is Q, then this is given by V into I into T, or we can write I square into R into T, or this can also be written as V square by R into T. So we can calculate the total heat generated simply using this expression. However, if the current is variable, then the total heat generated can be written as integral I square R dt. Integral I square R dt. As an example, let us consider series combination of bulbs. Let's assume that there are a couple of bulbs. Let's represent it like this. And these bulbs have different power. For example, this is P1, this is P2, this is P3, etc. And they are designed to operate at a voltage V. That means their rated voltage is V. Then the effective power dissipated is given by 1 by P is equal to 1 by P1 plus 1 by P2 plus 1 by P3, etc. So when the bulbs are connected in series, this is the equation. Remember, when the bulbs are connected in series, the least rated bulb glows brightest. A very simple idea, the least rated bulb glows the brightest. What if they are connected in parallel? You know, this is the preferred connection in domestic usage. This is the second bulb, here is the third bulb, and so on. They are all connected in parallel across a source. Let's assume that this is V. P1, P2 and P3 are their powers. They are designed to operate at value V. Then the net power dissipated is given by P1 plus P2 plus P3. And remember, in parallel combination, the highest rated bulb glows brightest. The highest rated bulb glows the brightest. So remember this very simple idea as far as the bulbs are concerned. As far as the bulbs are concerned, this is the idea. So these are some important concepts as far as current electricity is concerned. We will continue in our next session, in which we take up problems based on this. Today's chapter for our discussion is Atoms and Nuclei. First, let's take up the discussion of concepts, recap the important ideas, and go through the equations. And later we will discuss problems as well. So here, the important concepts that we are looking at are the idea of photoelectric effect. Then we will take up the discussion of atomic structure. Then we take up the discussion of radioactivity. And finally, the idea of nuclei. So these are the four important concepts as far as this entire chapter is concerned. First of all, the idea of photoelectric effect. Photoelectric effect. You know that Planck's quantum theory tells us that energy is always exchanged in integral multiples of quanta of light or photon. So this can be written as n times h nu, right? Or the quantum of each energy corresponds to h nu, or each energy quantum, each packet, each photon corresponds to an energy h nu. And h is Planck's constant, having a value 6.6 into 10 to the power of minus 34 joule second. And we know that from Einstein's mass energy relation, E is equal to mc square, and we can club them together to get mc square is equal to h nu, or the equivalent mass corresponding to an energy of h nu is m is equal to h nu by c square. Just like packet of energy, packet of light possesses energy, it also possesses momentum. It also possesses momentum. Momentum of each photon can be represented like this. Momentum of each photon is mc, and that is h nu divided by c square into c, or this can be written as h nu divided by c. Or you can also write it like this. This can be written as h divided by lambda, taking the earlier equation into consideration. So we can write momentum is equal to h divided by nu. Actually, the left hand side of this equation involves particle aspect of photon, its momentum, and the right hand side of this equation involves wave aspect, wavelength. So we can say that electromagnetic radiation exhibits wave particle duality. The wave particle nature can also be associated with a particle. It is the property of not only wave but also a material particle in motion exhibits wavelength. That means the corresponding wavelength given by de Broglie's wavelength corresponding to a particle is given by lambda is equal to h by mv, h by p, or this can also be written as square root of h by square root of 2mk. You know that momentum can be written as square root of 2mk. Many times we consider the particle in motion and its energy half mv square is derived from its accelerating potential, and the corresponding momentum can be written as square root of 2mqv. And correspondingly lambda is equal to h divided by square root of 2mqv. Suppose I consider an electron. For an electron, lambda therefore can be written as, if I simplify it further, I get 12.34 divided by square root of accelerating potential angstrom. So for an electron, remember the de Broglie's wavelength is given by this equation. In the case of photoelectric effect, a light of suitable frequency is incident on a metal surface, and because of this electrons are pushed out of the metal surface, and this process is called as photoelectric effect. Einstein's theory of photoelectric effect tells us that some minimum energy is required to push out these electrons. This minimum energy is what is called as work function. So we can say incident energy is equal to energy required to push the electrons, that is work function, and the rest of the energy appears in the form of kinetic energy or maximum possible kinetic energy of the photoelectrons. Suppose the incident light is of frequency nu, then we can write h nu is equal to h nu naught, where nu naught is the minimum frequency called as threshold frequency plus half m v max square, where v max is the maximum velocity possible. Photoelectric effect is explained by Einstein. According to him, the kinetic energy of the emitted electron increases with the increase of frequency. So if the frequency increases, then the kinetic energy also increases. The work function is constant, of course. The work function is constant. If the frequency of the radiation is kept constant and the intensity of the light is increased, then the photocurrent increases. the photocurrent increases. However, maximum kinetic energy remains constant. It does not change. It does not change. So with the increase in intensity of incident light, photocurrent increases, keeping the maximum kinetic energy constant. Now, if I consider a photoelectric effect, in order to stop the most energetic photoelectrons, we need to apply a negative potential. For example, if you look at this simple structure, this is where the photo or say incident light occurs, or say light is incident. Photoelectrons are released from this one and they are going to strike this plate. So this is kept positive potential, is kept negative potential. Now if I want to push these electrons just away, then I need to maintain it at a negative potential, this at a positive potential. So the negative potential to be applied is what is called as stopping potential. Stopping potential is the negative potential to be applied to prevent the electron from reaching the collector plate. How to get this? Stopping potential, I call EVS, is equal to maximum kinetic energy, and that must be equal to h nu minus W, or we can write this as EVS is equal to h nu minus h nu naught, where nu is the frequency of the incident light and nu naught is the threshold frequency. Some important graphs relating to photoelectric effect are here. Number one, the stopping potential versus frequency of the incident light can be shown like this. This gives you the value of V naught. So this gives you the value of V naught. Likewise, if I consider the intensity, suppose I consider say photoelectric current versus potential. The nature of the graph is something like this. So it becomes constant with the increase in frequency, with the increase in applied potential difference also it remains constant. And if you consider this one, this is V naught 1, this is V naught 2. So the applied potential difference decides the stopping potential, and this remains constant. The electric current or photoelectric current remains constant. So these are some graphs of photoelectric effect. Remember, this is a pretty simple chapter. The basic idea is very direct. In this chapter, the most important thing that you need to remember are like this. Number one, remember the basic idea of photoelectric effect. Secondly, remember the photoelectric equation. So if you remember these two ideas, this chapter becomes very direct. Okay. The second idea is the idea of atomic structure. Of all the important available atomic structures which explain the structure of an atom, Bohr's model is the most convincing one, intuitive one, and of course this is the earliest model which successfully explained the stability, mechanical stability and the electrical stability. According to this model, there are two postulates. Number one, first postulate tells us that electrons revolve around the nucleus just like a planet around sun. Then it tells us that the mechanical stability is provided by the electrostatic force, or we can say mv square divided by r is because of electrostatic force of attraction between the nucleus and the electron. So this is the basic idea. Of course, this was basically Rutherford's contribution. the first postulate of Bohr's model is about the stationary orbits. Electrons cannot revolve in all those orbits as suggested by classical theory, but only in those orbits for which the angular momentum is equal to an integral multiple of h by 2 pi. Or we can write this h, that is angular momentum, that is mvr, is equal to n times h divided by 2 pi. So, according to first postulate, the angular momentum is equal to integral multiple of h by 2 pi. The second postulate deals with energy when an electron jumps from one orbit to another orbit, or one energy level to another energy level. So, according to this, whenever an electron jumps from higher energy level to lower energy level, the energy difference is given out in the form of light of frequency or radiation of frequency nu. So, E2 minus E1 is equal to h nu. So, this is the second postulate. Based on this, a couple of important equations as far as Bohr's model is concerned are: number one, radius of the orbit. Radius of the orbit, nth orbit, is given by epsilon naught n square h square divided by pi m z e square. That's the radius of the nth orbit. For the first Bohr orbit, n is equal to 1, and for hydrogen atom, z is equal to 1. So, we can say the radius of the first Bohr orbit is given by epsilon naught h square divided by pi m e square. So, we can also say Rn is directly proportional to n square. That means the radii are in the ratio 1:4:9, etc. And radius is inversely proportional to z also. It's inversely proportional to z also. Velocity of an electron in nth orbit. Velocity of the electron in the nth orbit is given by z e square divided by 2 epsilon naught nh. 2 epsilon naught nh. And if I consider velocity of the electron in the first Bohr orbit, then this is equal to c divided by 137. So, in first Bohr orbit, the velocity is equal to c by 137 meter per second. Remember this one. And if z is constant, v is inversely proportional to n. And if n is constant, v is proportional to z. Energy. Energy of an electron in nth orbit. First of all, potential energy is given by minus 1 by 4 pi epsilon naught z e square divided by r, and kinetic energy is given by half mv square, that is z e square divided by 8 pi epsilon naught r. So, we notice that potential energy is equal to minus 2 times kinetic energy, and total energy is equal to minus z e square divided by 8 pi epsilon naught r, and if you compare this and this, total energy is equal to negative of the kinetic energy. Negative of the kinetic energy. This can be simplified further, and we can write as minus 13.6 z square divided by n square electron volt. I can substitute for r and I can obtain this relation. So remember this one, the total energy is given by minus 13.6 Z square divided by N square. Now depending on the transition from one level to another level, energy is given out in the form of radiation. Energy is given out in the form of radiation. This is given by this equation. For example, if an electron jumps from the level say N2 to N1, the electron jumps from level N2 to N1, then we can find out the wavelength of the light emitted, and we can also find out the frequency. The wavelength is written as 1 by lambda is equal to Rz square into 1 by N1 square minus 1 by N2 square, where R is Rydberg constant having a value 1.095 into 10 to the power of 7 per meter, of course. And for hydrogen, this is written as 1 by lambda is equal to R into 1 by N1 square minus 1 by N2 square. Depending on these N1 and N2 combinations, we have what are known as spectral series. Spectral series of hydrogen atom. First is Lyman series. Lyman series corresponds to N1 is equal to 1, N2 is equal to 2, 3, 4, etc. up to infinity. And we can write 1 by lambda is equal to R into 1 by N1 square, that is 1 square minus 1 by N2 square. This actually lies in ultraviolet region of electromagnetic spectrum. The series limit corresponds to N1 is equal to 1, N2 is equal to infinity. So if I calculate it, I get 1 by lambda is equal to R, or lambda is equal to 1 by R. The first member corresponds to 1 by lambda is equal to R into 1 by 1, 1 by 2 square, which corresponds to lambda is equal to 4 by 3R. So the range lies from 1 by R to 4 by 3R. Likewise, if I consider Balmer series, in the case of Balmer series, N1 is equal to 2, N2 is equal to 3, 4, 5, etc. And we can write 1 by lambda therefore as R into 1 by 2 square minus 1 by N2 square. And this actually lies in the visible part of electromagnetic spectrum. The series limit is given by 1 by lambda is equal to R into 1 by 2 square minus 1 by infinity. That gives us lambda is equal to 4 divided by R. And the first member of this corresponds to 1 by lambda is equal to R into 1 by 2 square minus 1 by 3 square. 1 by 2 square minus 1 by 3 square, which means that lambda for this is 36 divided by 5R. So the range of this Balmer series lies here. Likewise, Paschen series corresponds to N1 is equal to 3, N2 is equal to 4, 5, 6, etc. And we have bracket series. N1 is equal to 4, N2 is equal to 5, 6, 7, etc. And we have P-Fund series. P-Fund series corresponds to N1 is equal to 5, N2 is equal to 6, 7, 8, etc. And of course up to infinity. All of them terminate at infinity. So these are what are known as spectral series. These are spectral series. A couple of important definitions which are quite useful here are something like this. Number one, the idea of ionization. If during the process of excitation, what is excitation? Taking the electron from lower level to higher level. So if during the process of excitation the electron is completely removed from the atom is said to be ionized. So the process of removal of the electrons from an atom is called ionization. Ionization energy. Ionization energy is the energy required to remove an electron from an atom. The ionization energy required to ionize a hydrogen atom, is equal to 0 minus 13.6 electron volts or 13.6 electron volts. The same energy can also be expressed in terms of potential, and we call it as ionization potential, which is nothing but the corresponding potential difference required to accelerate the electron. This is nothing but 13.6 electron volts. Suppose an electron jumps from, say, nth level to lower level. For example, it jumps from nth level to lower level, that is ground level. Then the number of, or the possible number of spectral lines which are generated is given by n into n minus 1 divided by 2. N into n minus 1 divided by 2 is the possible number of spectral lines when an electron jumps from higher level to lower level, or say level n to ground level. The next idea is the idea of radioactivity. Radioactivity is a process in which spontaneous disintegration of the atoms of heavy elements takes place with the emission of alpha or beta or gamma radiations. So alpha or beta or gamma radiations come out. This is what is known as radioactivity. Now, during radioactivity, the given heavy atom disintegrates and it results in another fragment. We can call it as the child atom, parent atom and the daughter nucleus, parent and the daughter nucleus. Law of radioactive disintegration tells us at what rate does a nucleus or say nuclei disintegrate. According to Rutherford and Soddy, the rate of disintegration dN by dt is proportional to the number of undecayed nuclei. As it is a decay, we can write minus dN by dt. And dN by dt therefore can be written as minus lambda n, where lambda is a constant called as disintegration constant or decay constant This equation can be written in the following form: n is equal to n naught into e power minus lambda t, where n is the number of undecayed nuclei at some time t, whereas n naught refers to number of initial number of nuclei. So So we can write n is equal to n naught into e power of minus lambda t. Likewise, activity. That's the number of disintegrations happening per second, which is represented by A, is nothing but lambda into n. This can be written in the following form. I can write A is equal to A naught e power minus lambda t. Activity can be written in this form. These ideas lead us to the idea of what is known as half-life. Simple concept. The time after which the number of nuclei become half is what is called as half-life. Average life. So this half-life is represented by T. Average life is, or the mean life is, the sum of the lifetimes of all the atoms divided by total number of atoms. This T average is actually given by 1 by lambda. T average is given by 1 by lambda. And half-life is given by 0.693 divided by lambda. 0.693 divided by lambda. So T average is given by this particular equation, 1 by lambda. Some of the important equations which are quite useful are like this. N is equal to n naught divided by 2 to the power of n, where n and n naught are already known to us, and small n is number of half-lives. That means this n is equal to t divided by t, where t is the time. It is the time. The same equation can be represented in this form also. M is equal to m naught divided by 2 to the power of n, where m is the mass at time t, m naught is the initial mass. Likewise, activity can also be written in this form, A naught divided by 2 to the power of n, where the small n refers to time divided by half-life. Time divided by half-life. The idea of radioactive equilibrium. Radioactive equilibrium. In a radioactive series, at the stable equilibrium, the rate of decay of any radioactive product is just equal to its rate of production from the previous member of the series. That means, if I consider n1 and lambda 1, n1 lambda 1 is equal to n2 lambda 2, or n1 divided by t1 is equal to n2 divided by t2. So remember this one, in the case of radioactive equilibrium, then the rate of production, the rate of decay are equal to each other. They are equal to each other. This is a simple concept but quite useful while handling numerical problems. Nucleus, nuclei. This part is more of memory and information based. Nucleus of an atom is positively charged and the radius of a nucleus is approximately 5 into 10 to the power of minus 15 meters. The size of the nucleus, as said, size of the nucleus is of the order of 1 Fermi. Its radius is this much. Radius of nucleus in general is given by r is equal to r naught 8 to the power of 1 by 3. What is that r naught? R naught is 1.3 Fermi. It is equal to 1.3 Fermi. And A refers to mass number. A refers to mass number. density. Density of a nucleus is given by mass of the nucleus divided by volume of the nucleus. So I can write A into mass of proton divided by 4 by 3 pi R naught into A to the power of 1 by 3 cube, and this simplifies to MP divided by 4 by 3 pi R naught cube. And this is approximately equal to 10 to the power of 17 kg per cubic meter. That's the average density of a nucleus. That's the average density of a nucleus. One of the important concepts which is quite useful for handling problems is the idea of atomic mass unit. Atomic mass unit, represented by AMU. This is equal to 1 AMU is equal to 1/12 of the mass of carbon nucleus. And this one atomic mass unit is equal to 1.67 into 10 to the power of minus 27 kg. With the help of mass energy equivalence, we can find out the corresponding energy. And that turns out to be E is equal to mc square, and you can also write it as h nu. Suppose I consider the idea of mass defect. What is mass defect? The actual mass of the nucleus is always less than the sum of the masses of its constituent particles. This difference in mass is known as mass defect. So this is given by delta m is equal to z times mass of proton plus a minus z times mass of neutrons. This is mass of the nucleus minus its actual mass. So this difference is called as mass defect. And corresponding to mass effect, if I convert that into energy, the energy I get is known as binding energy. The energy equivalence of mass defect. So how do I get that? So corresponding energy is given by delta m into c square, and if I simplify it further, then binding energy turns out to be delta m into 931 mega electron volts, 931 million electron volts. So corresponding to a mass defect of delta m, corresponding energy or binding energy is delta m into 931 million electron volts. And many times we use this idea, the idea of binding energy per nucleon, which is nothing but delta m into 931 divided by a million electron volt per nucleon. This binding energy per nucleon depends on mass number, and if you plot a graph of specific binding energy, that is binding energy per nucleon versus mass number, then the graph that we get is of this form. The graph that we get is of this form. So corresponding to a mass number of 50, we notice that binding energy per nucleon is maximum. That means it gives you a quotient of stability. So corresponding to this, you notice that this is the most stable part. This is the most stable nucleus. A nucleus may undergo decay, or say it may undergo a change if a heavy nucleus is considered from the graph, you notice that heavy nucleus is not stable, it is unstable. It splits up into lighter nucleus or say lighter nuclei. And this involves liberation of energy. This process is called as fission. So during fission, the heavy nucleus which is unstable splits into medium sized nuclei or say smaller nuclei. It's called as fission. Conversely, if I consider light nuclei, they may merge to give a heavy nucleus. And this also liberates energy. This process is called as fusion. So during fusion, this is precisely what happens. And this fission and fusion are basically the processes involving or say processes in which energy is liberated. And if a chain reaction takes place, then it is basically a self-propagating process in which a number of neutrons multiply rapidly during fission until the whole of the fissile material is disintegrated. And to start a chain reaction, a minimum mass of the fissile material is required. This is called as critical mass or critical size. These are some basic ideas as far as atoms and nuclei are concerned. Remember, this is a pretty easy chapter. Most of the ideas are very simple, very direct. It's basically memory stuff. You need to remember a couple of equations, and with the help of those equations, you can try problems.